Hello and welcome to my report of Lab 3. The purpose of this laboratory experiment was to first calculate the mass of a black hole using predictions of changing momentum and curving motion, and to model the orbit of a star around this black hole, and then to model the orbit of a spaceship around the moon, which was also orbiting another planet. To do this, we used ClosScript, and some fundamental physics concepts needed and used throughout the experiment were Newton's second law and Newton's law of universal gravitation. So since this lab was completely computational and mathematical, there were no errors. However, we did make some assumptions. So for part 1, we assumed that the black hole was stationary and that the only force present was the force of attraction due to gravity between the black hole and the star. In part 2, we assumed that the planet was stationary, although we initially said that it was supposed to be orbiting the star. And we also assumed that the only forces present were the forces of attraction due to gravity between the ship, the moon, and the planet. So for part 1, we were given the mass of the star, the initial and final velocity of the star, and its initial position. With this, we were able to calculate its momentum, the rate of change of the momentum, the net force acting on the star, and we were also able to update iteratively the position and velocity of the star. And finally, we were able to calculate the mass of the black hole, which was ultimately the purpose of this part of the experiment. So using the values for the mass and the velocity that we were giving, we were able to calculate the momentum of the star, and then when we were able to calculate the change in momentum, and then the rate of change of the momentum. And from Newton's second law, we have that the net force is equal to the rate of change of the momentum. And using the net force, we were then able to calculate the mass of the black hole. It is important to note that since the path at which the orbit of the star around the black hole is not perfectly circular, it's more of an elliptical path, this net force isn't constant, and neither is the position of the star or its distance to the black hole. So therefore, this calculation of the mass will not result in the same value for every new position of the star. And therefore, to get a final concrete answer, we took all possible values for the mass from each position of the star and took the average of all these possible values for the mass, and we used that as our final answer. And this is what it all looks like modeled in ClosScript. So in yellow, we have the star orbiting the black hole. For part 2, we were given the mass of the ship, the planet, and the moon, and the initial position of the ship, the planet, and the moon, and also the initial velocity of the moon. With this, we were able to calculate the net force on the moon, the net force on the ship. We were also able to update the position and velocity of both the moon and the ship. And then we calculated empirically the initial velocity of the ship by just placing values for the initial velocity until we got a model that was correct. So under the while loop with the given conditions, we were able to calculate the net force on the moon and then the net force on the ship. And using these net forces and the given delta t, we were able to calculate and update the velocity of the moon iteratively and its position, and also the same for the ship. And this is what it looks like modeled in ClosScript. So in blue, we have the planet fixed at the center. Then in cyan, we have the moon orbiting the planet. And then in magenta, we have the ship orbiting the moon. So our results are that the mass of the black hole is approximately 1.29 times 10 to the 29 kilograms. And a velocity of the ship, initial velocity of the ship that worked, and the one that was used for this experiment, was just 160 meters per second in the y direction. So some post-lab conceptual and analytical questions. What is the difference between the net force and the rate of change of momentum? So from part 1, if you remember correctly, we set them equal to each other because they're mathematically equal. However, they are different conceptually. The net force is what causes the momentum to change. And then the rate of change of momentum is the measure in the change of momentum with respect to time. So put simply, the net force is the cause, the change of momentum is the effect, and the rate of change of momentum is the measure of the effect over set intervals of time. And what's missing in the computational model to include the entire system? So the black hole, the star, the planet, the moon, and the ship, all modeled together. So we would have to include the force that the black hole exerts on the planet, the moon, and the ship, and the force that the star exerts on the planet, the moon, and the ship. And then with these forces, we include those in the net forces to get the correct forces, and we would have a final model which would have the black hole centered in the middle. Then we have the star orbiting the black hole, and then we'd have the planet orbiting the star, the moon orbiting the planet, and the ship orbiting the moon. So that would be what we'd have in the entire model. That has been all. Thank you for your time.